we start?
Yes, start, yes.
Great, okay. Hello, hello. Happy to see you after the weekend. So the first thing I want to say is that Jura was right. In my last lecture, I kind of said that in Gromov squeezing, we constructed a certain sphere, right? Important, nice, holomorphic sphere. And I said it's embedded. But so in dimension 4, one can prove this. And in high dimensions, one cannot prove it. And more important, one does not need it, right? You just need to take the area over the domain defined by the pullback of the map, and that's it. Great. So embeddedness is really not needed. A Noble junction formula, it would be horrible because then Gromov squeezing would be known only in dimension 4. Okay, so today we have very ambitious program, but before that, I wish to make an application. So I have not given many motivations for symplectic embedding questions. In this text, you may have seen there are some 6 or so, but now that we have proven something, I want to give one motivation. I heard Gromov was also intrigued by that, and that was one reason he looked at embedding problems. So it is about super recurrence. So let's look at the following problem. You take, so you remember, everybody did the exercise and proved Gromov two-ball theorem. Great, great. Yeah, great. Okay, so when you have two balls, they are relatively small. It looks exactly like in dimension 1, right? So these two areas in dimension 1, you have this picture. And here in any dimension, it looks also exactly like this, because the constraint is exactly on cross sections, so exactly like in dimension 2. And of course, this constraint is very much stronger than for volume preservation when you compute it. Right? So let's do an application. Let's take a ball and let's take a Hamiltonian system defined on that ball. For instance, because the Hamiltonian vector field along the boundary is tangential, right? Just a self-map of the ball that preserves the ball and the flow exists for all times. Something like this. Somebody move somehow. No, okay. Okay. So now I take a relatively, probably there is a light problem here. So I take a ball here in, a smaller ball, a set of initial conditions, and I ask myself, what can I say about the image? Does it intersect or not? So if this smaller ball is relatively large in the sense that 2 small a is bigger than big A, if you have this condition, then they must intersect by Gromov two-ball theorem, right? Okay, so you have this intersection. Now, let's remember how you prove Poincaré recurrence theorem. So in Poincaré recurrence, you look situation like this. So you take some set, and then you take initial condition, and then it somehow moves. It moves, but by volume reasons, after some point, 2 of the image balls must intersect, and then you look at the primage of that iterate, and then you know that from this initial condition, some point must have intersected, right? So this is the very basic idea of Poincaré recurrence. If you would apply Poincaré recurrence by only remembering that this map is volume preserving, you could only conclude that for some iterate k less or equal than 2 to the n minus 1, you do come back. But in this symplectic situation, for k is actually 2, you immediately come back, right? You immediately must intersect. So this is sometimes called super recurrence. There is a very strong recurrence property of a Hamiltonian system that usually is expressed in saying that there are many closed orbits. But here, in the sense of Poincaré recurrence theorem, the recurrence is also much stronger. Is it kind of clear? right? So if you only have a smooth dynamical system, it's very easy to construct examples where they never intersect. You can go in, you can go in. If you have volume preservation, you get some stronger recurrence, but from these embedding obstructions of symplectic mappings or Hamiltonian systems, you get super recurrence, right? So this is just one example. Whenever you have an embedding obstruction, you can translate it into a super recurrence of Hamiltonian systems. Fine. Okay, so this was one motivation. Now, here is more light. Yeah, these patches, sorry, we'll see. So, okay, so can you read it? Maybe I just let you read this. I clean the other one.
Yes, it's readable. It's okay. Yes.
I just let you. Can you read it?
Yes, I mean, yes, I can read it. Yes.
I let you read a little bit.
Yes, it's okay.
I clean the other one.
Okay.
Okay, so this is the goal of today. We wish to prove a much more general symplectic embedding theorem. So we take as a target, not a cylinder like in Gromov non-squeezing, but a ball. And we take any collection of balls here, finite collection of balls of arbitrary size, and wish to know what is the smallest target ball so that they fit, right? And from here on, everything is in dimension 4. And I want to say that dimension 4 is really important here because at several places we need positivity of intersection and other insights that are true only in dimension 4. So from now on, everything is dimension 4. Okay, so this is our problem, and the result is that, the light. So the result is that these balls embed if and only if two things are true. And the two things are completely numerical. Okay? The two things are this and this. And here is a 4 because the proof will have a 2 and a 3. The proof is a somewhat long translation of things. So this is a completely symplectic statement. It's a question whether a collection of balls can embed into a ball. And here we have just completely numerical statements. Okay?
Felix,
questions?
I would like to see the formula. I would like to see the Diophantine equation. I would like to see it.
Yeah, okay. So this is the problem we want to solve, right?
Yes.
It's called 1, and from now on, for the rest of everything, this is 1. And the Diophantine system is this. Yet. So
how many conditions are there? Okay.
Pardon?
How many conditions are there actually?
2.
Like
this,
one, and then one below, and what are the lower one? The DE, the DE. What is the relation of the equations of the system below the statement?
Okay.
Okay, you explain us. Yeah.
Yeah, there are 2 things to be checked. You can embed if and only if the sum of the HA square is less than A square. So this is actually obvious. Well, let's first check this direction. So if this is true, can somebody tell me what the volume of this is? I tell you, it's a to the n over n factorial. So, and because n is 2, this up to divided by 2 is the volume, right? The volume of the 4-ball is pi r squared to the 2 over 2. But this a is pi r squared. So this up to a 1 over 2 is the volume. And this up to a 1 over 2 is the volume. So it means that this condition is the condition that the volume is not bigger, right? Maybe I say it. So this is volume condition. It's obvious condition, right? So this condition is the condition that comes from obstructions of holomorphic curves. I will explain, but the deep part of the theorem is that this is complete. There are no other obstructions. If the volume obstruction is fulfilled, and if this holomorphic obstruction is fulfilled, then there is a symplectic embedding. So this part here is deeper than this part. Okay? Mm-hmm. So this here is the holomorphic constraint part. And let me explain. So it must be true that something, namely 1 over d times the sum of mj aj is less than a for all solutions of a certain Diophantine system. Now, so what is the Diophantine system? It's that the sum, so you look at solutions of a Diophantine system. Let's do abstractly. Diophantine system means that you are looking at polynomial equations for integers. So here it is that the variables are mi, mj, and d. The sum of the mj should be 3d minus 1, and the sum of the mj square should be d squared plus 1. I will say where it comes from, okay? And then if you have a solution, you do something. Namely, you write some mj aj divided by d, and it should be less than a. So this gives a constraint on this a, right? Mm-hmm. That's it. Good. So now we will see in detail what it means. But what it means is you only look at holomorphic spheres that are embedded. A holomorphic sphere that is embedded has a certain Chern class, namely 1. And this condition here will be exactly that. And this condition says that the self-intersection number of such a sphere is -1, which is also automatic. So this condition means that we have given a holomorphic sphere somewhere, where I have not said yet, an embedded holomorphic sphere with self-intersection -1. And then such a sphere, because it's holomorphic, the symplectic form must integrate positively over it. Because it's symplectic, it's a J-holomorphic sphere for a good J. And this positivity is written here. We will come to it. So all this here only says that this is the list of constraints of embedded holomorphic spheres. And this is the volume constraint. So now that I have said what this is almost clear. But the other direction is hard because there could be many other constraints from other holomorphic submanifolds and maybe more than that, right? But it's a fact that already the embedded holomorphic spheres see all constraints up to the volume. The volume must be named. Is the statement clear? So this will take some more than one lecture. No, about one, okay? Good. So
I hope you don't erase it.
Yeah, at some moment.
You won't be able to remember.
But you can learn it by heart.
No, not me, no.
Okay, I will now, I will show it again. So for 15 minutes, we do something a bit boring. We use the theorem to check the table of the first lecture. You remember the table? It said that k equal ball go into a given 4 ball for a given k if, well, the maximal packings we can get, right? There was this 1, 1/2, 3/4, 1, 5 over 4 over 5, and da da da, so 63 over 64. And this table we now check. Well, I could also give it as an exercise, but I want to show you a little bit how you work with such a result. And yeah, okay, let's do it. So the corollary is that, yeah, well, they don't write. So the corollary is that the table T is okay. Table T was this table you remember by heart, right? It was, you know, it was something like for k equal to 1 ball, there you can fully fill, and then for 2, 1/2, and then for 3, 3 over 4, and so on. And then for k bigger or equal than 9, you can fully fill. You remember that? So we will prove now this table. Okay, so, okay, let's take a solution. Proof. So I take a solution. So this given time system for k. So then I write something very simple. So I write 3d minus 1. And now I use one equation. So it is the sum of the mj So I have used one equation, right? And now I use, maybe it's called Chebyshev inequality, something well known. So it's less than k times the sum of the mj. Right, so this, it's easy, but you saw it once. And this, and now I use the second equation. Right? Okay, so now I rewrite it. Okay, so now the great thing is that this has finitely many solutions for k less or equal than 8. You just look at the, well, don't know, the discriminant. And therefore, there are only finitely many solutions if k is less than 8 for this. And these solutions you just find in 2 hours. You just find them, okay? So this has finitely many. Yeah, you see, because of this term, right? So it has finitely many. So you see there is a problem. If there are infinitely, I mean, what we have to do according to our theorem, we have to find all the solutions and check their constraint contribution and then find the biggest one. But if there are infinitely many, this is a bit difficult. So I first want to understand for which k I have which solutions. And for k less or equal than 8, so for at most 8 blow-ups, comes later, for at most 8 balls, I have only finitely many solutions. So then I can just evaluate on a given tuple and see what I get. So now I write them down. When you do it by hand, it takes 2 hours, but let's do it. So they are So I give you now the list. It's a bit boring. So if D is equal to 1, then there is only 1. No, wait. Okay, if K is equal to 2, let's do it. Let's do one example together. Let's assume K is 2. So here we have 7D squared minus 6D minus 1 is less than 0. From this, you immediately find that you must have M1 equal to 1, M2 equal to 1, and that's it, nothing else. So immediately, right? And then for K equal to 3, 4, there are no new solutions. Of course, you could always take M3 or M4 equal to 0. That's okay. But then for K equal to 5, there is a new one. So in this 1, 5 means that I mean 1, 1, 5 times. It means D is equal to 2, and then M1 till M5 are 1. Okay? This is a solution of the Diophantine system. And then for K equal to 7, there is a new one. And this takes really just 10 minutes to check that there is nothing else. And then for K equal to 8, there are 3. Okay, it's not very exciting, but you just find them. So now we have found all the solutions for K less or equal than 8. So now we can very easily find, for instance, 6 balls, what is the biggest size that embeds into a given 1 ball. Because we just check all the constraints for K less or equal than 6, right? Okay, let's do it. So for instance, for K equal to 2, there is only 1, namely this one. Okay, so what is the constraint? Well, this one, the constraint is 1 over D, which is 1, and then what? And then, you know, this constraint, right? MJ, AJ. But AJ is small a, it's always the same here. So here in this table T, the small aj are all the same, right? So the constraint is that 2a is less than a. And there is no other constraint. And this is, of course, exactly the Gromov-Toubeau theorem, but you can also realize it, right? So we have found Gromov-Toubeau theorem in the special case in dimension 4 the second time. Okay, so let's do K equal to 5. So we already have this constraint. We should not forget it because we can take 1, 1, 0, 0, 0. But we have one more, namely this one. And this gives the constraint that A is at least, well, 1 over 2, this is this, and then 5a. And this 5 over 2 was in the table T. This is the 5 over 2, and this is sharp by the theorem. You can realize it, and actually we have done it by hand in the first lecture, right? We have checked that you can do this, 5 over 2. You remember? There was a picture. Okay, So let's do one more, maybe two. So k equal to 7. So we have one more constraint, this one. And always the new guys, they're actually stronger. They happen to be always the new maximal constraints. So this time we find, so this time 3, this one, 2, 1, 6 gives the constraint that A is at least 1/3, this D, times 8A. Because you see there are 8 balls. Here is, no, something is wrong. Why is there an 8? Okay, I'm a bit confused. Something is maybe wrong. Very strange. I don't know. I cannot find now. Okay, and this implies that P7 is, well, it's 7 times 3/8 squared, which is the famous 63/64 that we have seen before. Okay, so k equal to 8, you can do yourself. So what happens is that the biggest constraint is the strongest. This one, right? You have to compute 3 constraints in addition. Well, all these and this and this and this, and this is the strongest. And you get that P8 is 288/289. Now it takes 5 minutes. You have to compute all constraints, but there are only, I think, 7, and then it comes. Okay, if you do that in detail, well, you have kind of fun because you make mistakes and get contradictions, but at the end, it's, okay, good. But now somewhat nicer is that from this theorem, we immediately get that for k at least 9, there are no obstructions. And you see, this is fortunate because for k at least 9, the Diophantine system has always infinitely many solutions. So if you should really use them, it will be very hard. But fortunately, you do not need because of the following. So if k is at least 9, so then the constraint from a solution we get the following. We get that A is at least 1/d times A times the sum of the mj. So I use here that the AI in this problem are all the same by assumption, right? Okay, so now I use only one of the equations. So this is the same as A/d times 3d minus 1. But this is less than A/d times 3d, which is 3a. What do I do? No, this I don't want. So now I use that k is at least 9. Right? My assumption. Well, but this is, okay, so this is a root of k. So it means that whenever we have a holomorphic constraint, right, these are all the holomorphic constraints, it is actually weaker than the volume constraint. So the only constraint, the strongest of all constraints, is the volume constraint. So there is, but the volume constraint says that we cannot fill more than everything, so we can fully fill, right? So weaker. So you can fully fill. Every holomorphic constraint is weaker than the volume constraint, which means that you can fully fill. You can fill all of the volume. Fine. So this is quite fortunate because it means that we do not have to understand the infinitely many solutions, right? Okay, so do you know it by heart now? I will, okay, I give you 1 more minute. So now I want to prove this. So it will go like this. We start from this, and then we prove 2, and then 3, and then 4. And today I hope to go to 3. But this is the goal. And what I like about it is that this is a geometry problem. 2 will be the problem of realizing a certain cohomology class by a symplectic form. So it's a cohomological realization problem. 3 will be something already completely homological. Nothing about symplectic, not geometric anymore. A completely homological statement. And 4, well, it's a number theory problem somehow, right? So it gets easier and easier and more combinatorial algebraic. So this is geometry, and the next step is something about homology realization of blow-ups, and we will see. So does everybody know what a complex blow-up is? Yes.
Reward.
Jura, do you know?
I do.
Great, so we can skip it.
No.
You saved my day. Okay, so I will say in 1 minute what a complex blow-up is, and then the difference of this to what a symplectic blow-up is. So one should preparation blow-up. So in complex geometry, blow-up, as you probably know, is something great because you can get rid of singularities. When you have a singularity, sometimes, or by Hironaka always, you can blow up. So you go to a bigger space, and the singularity, which maybe looks something like this, so things become disjoint. And the idea is simply to say, at this point, we don't keep the point, but we insert all directions. And since directions are different, singularities go away. That is essentially the idea. So, okay, so in the complex world, it's enough to look at the local model, Cn or C2. So complex. So you replace a point, but I can assume 0. And I only do it in C2. You could do it in Cn. Well, by all complex lines, by all complex directions of that tension space, by all complex lines. There is, of course, also a real version, but of this tension space, right? So in a way, it looks like this. You have C2, and then this is replaced by all lines, by all these complex lines. So the space becomes bigger, right? Good. So yeah, great. So now first I want to see that at a totally topological level. So topologically, maybe I'm a bit fast. So topologically, you can do the following. Instead of taking out a point and then reinserting all complex lines, you can take out a fixed ball, open ball, and then look at the boundary, which is a 3-sphere, and then replace every Hopf circle there, collapse it to a point. Maybe I should write that. So topologically, you can do it, you can describe it in a different way. Let's forget that. You can do equivalently the following. I mean, topologically, then you see in this complex blow-up business, on the blow-up, you want to put a complex structure and get a complex manifold, and then you have a projection, and it's a biholomorphic map away from this point and these lines. So, but now I only look at the smooth part. So you can do equivalently the following. So you remove a ball, an open ball. Whether I remove an open ball or a point is topologically the same. And then the boundary of this removed ball is S3. And S3 you see as foliated by circles, right? It's a circle bundle over S2, the Hopf vibration. So it is, this guy is foliated by Hopf circles. So what is Hopf circle? Yeah, we saw it before. It's just a Hopf circle is a set of the form alpha Z1, alpha Z2, where alpha is on the circle, runs through the circle. And Z1, Z2 are describe a point of norm 1, right? So, and yeah, no space. So, and this is of course exactly the intersection of S3 by a complex line, right? So this is exactly the unique complex line going through Z1, Z2, contains the whole circle, and that's it, right? So this is F3 intersecting a complex line. I don't write it. So from this you see that these two descriptions are the same. Okay. So now the second point of R, now we should also collapse it. So then you collapse, you replace every Hopf circle by a point. So now you collapse. It means just replace. So you along these circles to CP1. And if you take S3 and quotient out by the Hopf vibration, you get exactly S2, which I see as CP1. So somewhat schematically, it looks like this. So here, in a way, you have C2. And then I take out the ball, but the boundary of the ball is foliated by circles. And they are all disjoint, these circles, not like in the picture. So this is a foliation of the boundary of the ball, S3. So the ball is already gone, and now this boundary is collapsed and becomes something like, well, the picture is somehow like this. So you have topologically CB2 or C2 without a point, and the point is replaced by embedded two-sphere. But the two-sphere is not as normal as you think. It has self-intersection number -1. It's a computation say, not so hard to see. So maybe I just write it. So there are two facts. One fact is that this CP1, this one, intersected itself is -1. So that it is 1 or -1 is not hard to see, but the sign is a bit boring. And another fact is that topologically, you can see this space also the following way. This is sometimes useful. So this is exactly C2 and then blow up with CP2 oriented. So you take the space you have, right? The C2 is just a local model. We can do it with any symplectic, well, with any even dimensional manifold action. And then we take connected sum with CP2, but when you do connected sum, orientations are important. So I invert it with the wrong orientation.
Sorry, something is wrong. Something seems to be wrong there. I mean, it's not S2. What is it? Sorry. C2. Sorry, I didn't see.
C2. So
right.
This is somehow just locally our four manifold. And this we call maybe blow up of the space. So blowing up topologically is the same as taking the dimension, complex dimension 2, the connected sum with CP2 with the wrong orientation. But for us, this picture is important, that we take out the ball and we collapse the boundary, the S3, along the Hopf vibration. And we get an exception, so-called exceptional sphere, an embedded two-sphere, which is non-standard embedded. It has intersection number -1. Fine. Do you like that? Alexei? Not so much.
So for me it's okay, but now I would like to learn the symplectic version.
Exactly, now comes the symplectic version. For a complex geometry, he probably knows the very last statement, that is this connected sum with CP2, but he always thinks of take out the point and replace it by the set of directions through that point at the tangent level. But symplectically, it's very important that we take out the ball, because we want to put back on the new space a symplectic form. And the kind of the form we put there will crucially depend on the size of the ball we have removed. Because we want to use this construction in order to say something about embeddings of balls of given sizes. So size in the symplectic version plays a role, right? So the same symplectically. We can do something similar, almost the same, symplectically. Okay, so again, now you start with a ball, or let's say the symplectic image of a ball. It's not so important. So you start this time from a ball in C2. And this C2 is the standard R4. Okay. So now we can form as before by removing the ball and doing the collapse. We build a new manifold, at least at the smooth level. But the key is that there is a really up to diffeomorphism, up to symplectomorphism, a unique form with good properties on the blown up space. So there is a symplectic form and I call it omega A on the blow up. Such that what? You see, outside of the ball, I don't want to change what I already had. Such that it is the old thing, the usual one. Well, you have to do a little neighborhood thing. You have to have you need a little annulus around the boundary. Okay, on, let's say, outside. A little neighborhood of the ball. Yeah, I'm not very precise. You have to take actually an embedding of a closed ball that extends to the A plus epsilon ball, and then you have to do something with neighborhoods. So this we want, that outside we do nothing. And what we also want is that, so we have this exceptional sphere, and we want that the new form integrates on the exceptional sphere to what we expect, namely to A. Right. So this, well, this you expect from the Hopf vibration, right? So when you do the symplectic reduction to describe the Studi-Fubini form on CP2 on a CP1, you exactly get this A. And this can be done. So it's a little bit tricky because you have to discuss uniqueness and how you do exactly the interpolation. But it is written in 10 great pages in the 3rd edition of Dietmar, Salomon, and Dusa's book. And first it was 1 page, and then 5, and then 10, since Dietmar was very unhappy with it. Great.
So, Felix, do you mean that you take the boundary and you take the usual symplectic reduction by taking quotient by kernels? And
yeah, exactly. It looks exactly like that.
And this makes sense. The integration of like this makes sense along just cross sections, and then you pass this together, and what you get it's something like this.
Yeah, it is exactly like this. You see, I should have done it. It takes 20 minutes, but it was an exercise in the proof of Gromov-2-ball theorem. You need that inside anyway, because the proof in Gromov-2-ball theorem is in CP2. And first you have to understand that the usual form on when from CP2 you take out the line at infinity, you get exactly symplectically the 4-ball with the usual symplectic form. By the way, the Studi-Fubini form is constructed. Yeah, it's very precisely written in, for instance, Audin's book, for instance. But it is essentially clear because you said it. You mod off the kernel, so what is left is perfect. And if you write out things, you get what you expect, size A. Okay. So indeed, something in this direction we will now use. So I say recall, but maybe it's not so clear. You see, we will actually not, our target space is this ball, but we must compactify it to CP2. Otherwise, we cannot do J-curves well there. So this is symplectomorphic to CP2 of size A without the CP1. So you take any line, you take it away, and then you see, when you know moment maps, it's clear, right? When you do you take that away. So it's exactly that picture. But this, you can also write down a formula. You simply write down embedding. So I can do it if A is 1, or maybe pi. Maybe pi's are wrong. You do what? You take Z1, Z2, and you just map it to Z1, Z2, 1 minus Z1 squared minus Z2 squared. So this mapping, so this is if A is pi, and otherwise you scale a bit around. This mapping is symplectic. And on the right-hand side, I mean the Studi-Fubini form. And what you miss is exactly one of the coded CP ones. So the fact we will use all the time, and during the proof it will become also clear, is that the problem we want to solve well, this sits here right now. So this problem is equivalent to this. So it's not obvious. If you make a space bigger, it could be that you can embed more. Actually, there are examples where it happens, but here not. The reason is that what you add is symplectic. If it would be Lagrangian, there are easy examples which show that if you make the space bigger, suddenly you can embed much more, like when you pack tori. But here not. So it will become clear from the proof that you cannot make this A smaller by taking CP2. And from now on, we will only work with CP2 as a target. Are there any questions? Okay. Okay, sorry, since this is a bit long, I need to be a little bit boring here. So I need a little bit of notation. We will now go to the blow up of CP2, right? So we will transform the problem of embedding balls into CP2 in a problem of realizing certain homology classes in k-fold blow-ups of CP2 by a certain symplectic form. So now I need a little bit of notation on the k-fold blow-up of CP2. You take CP2, locally you do exactly like before, C2, but you do it k times. Okay, so my notation is as follows. So L is the class of a line. So this is in H2. Which is, of course, it's a generator, but it's my positive generator. Okay, so now I've blown it up k times. So I take my CP2, I blow it up k times as before by, well, for now in a topological way, but later with weights. And I call this new space MK. For now, it's just a smooth manifold. It's diffeomorphic to this one. Okay, so now I briefly say what the cohomology ring of that space is. It's easy. You see, when you do one blow up, you get this new exceptional divisor, and it's holomorphic, so it's certainly homologically essential. So this is called EJ. So it's the homology class of the J. Exceptional divisor. It's sometimes called exceptional divisor or exceptional sphere, as you like. Right, just when this CP1 we got from collapsing the S3 along the Hopf vibration, it was an embedded S2 with self-intersection number -1, and in homology it represents a certain class, and it's called EJ. So now, what is the homology, the second of this space? Well, if I don't blow up, it's generated by the line, right? And for every blow up, I get a new one. So I get, it's generated by the line, and also E1, and also EK. So, very good. So what is the intersection form? How do they intersect these classes? Well, you see, they don't see each other because I can do the blow up where I want. I'm not crazy and do the blow up on a sphere I already had before. I do it disjointly, and it's totally local because I embed a little ball or even just a point and do this collapse. So it's clear that they somehow are disjoint, right? So if this is MK, I have here maybe L, well, the sphere that represents L, and then the others are disjoint because I can do it wherever I want. So they don't see each other. It means the form is diagonal, and the self-intersection, well, LL, as you know, is 1. And, no, sorry, yeah, I'm always confused. LL is 1 because, yeah, by the first fact of projective geometry, right? Two lines intersect exactly once, also the line itself. And the other ones we have seen -1. So the intersection form is L square is 1, and EJL is 0, and EJ squared is -1, and EJ EK is minus delta K JK. They don't see each other. Good. It's very boring, but we need that. Okay. Good. Now even more notation, and then it's done. So we also need to know, we need more notation, sorry. So I denote by small l the Poincare dual of L. So this is in H_2. And everything is integral for now. Okay, so just the Poincare dual, and EJ are the Poincare duals of the EJ. Okay, we need that because we have to do something about the first Chern class. So what is the first Chern class of this space? So you probably know what happens if K is 0. It's 3 times in CPN, it's n+1 times the Poincare dual of the line. So it is 3L. And then for the other ones, it comes from the intersection form minus E1 minus EK. We need that. And then sometimes it's also good to look at its Poincare dual. This is called the canonical class. but it's minus the Poincare rule. So it is minus 3L plus. So with the signs, one has to be a bit careful. One can make a mess. Okay. So that was very boring, I know, but we will need it for the whole rest. Good. So now I can finally start. So I can translate the problem of symplectically embedding the collection of balls into a given CP2 into another problem. So this is our step one. It says that our problem of the beginning well, we have already seen that this is the same as to go to CP2. So this problem is the same as the following. 2. That the following class A times L minus the sum of the AJ, EJ. So what is this? This is the cohomology class, right? On this blow up. But this is now a real class. I write down this cohomology class, right? So what do you think about this class? This is not the class of the symplectic form. This is just a cohomology class. And I say that I can do this embedding if and only if this class can be represented by a symplectic form. Okay? So you can hope for that, because when you have CP2 and you, so what is the form if you do no blow up? Yeah, it's this, right? The usual form. The usual Studi-Fubini form of size A is this, represents this. And now when you do a blow up, by what you have said, we do that. It's for an embedding of one ball of size A1, of small A1, we get minus A1 E1 in cohomology. So if we can embed this, we get this. So this direction we already know. But the converse is actually true. Is the statement clear? Any questions? You see, here something important happens. So this is a completely geometric problem about balls, or if you want, balls in CP2. So this is something very different. A priori, it's a bit crazy to go to a much more complicated manifold, the blow-up of CP2. But the problem is different. It's not a symplectic embedding problem. It's a question whether you can realize a given cohomology class by a symplectic form. And this kind of questions is a main topic in Kähler geometry. It's about understanding the so-called Kähler cone. You have a complex manifold. You want to find out whether it's Kähler. You find one Kähler form, and you want to know which homology classes can be represented by Kähler forms. And here, our manifold is Kähler, but we don't want to represent by a Kähler form. that would be much too restricted. We want to represent by symplectic form, which looks analogous. The techniques will be different, but the question is very close to a very traditional question. Okay? In the Kähler setting, this is called Nakai Mordechon criterion. It's super classical and there's many different proofs. But we will need something very different. We need Taub's Gromov theorem. Okay? And so this is really a main step. Okay, so let's prove it. No, it's called Nakai-Moishetson criterion in the Kähler world. So this direction we have already proven. When we embed a ball, we can construct on the blow up a symplectic form. We have not proven it, but described. This is the 10 pages in the new book by Dietmar. But the other direction is a bit more subtle. So the point is that you can, instead of blowing up, you can try to do the converse. When you blow up, you do what? You take out a ball, collapse, and get an embedded two-sphere. If you have a good embedded two-sphere, you can try to take it out and sew back in a ball. This is called blowing down. And this is indeed always possible in exactly bijective force and back way. But that is really so is actually a bit more tricky than let's do it. Okay, so there is this part is true because there is a converse construction or reverse construction. So I just do it independent of what we have in our situation. It's called blow down. And it goes like this. So what do we need? Yeah, we need a symplectically embedded sphere of self-intersection number -1, because the normal bundle must look right. Otherwise, we cannot. It's a surgery operation, so the normal bundle must be correct. And if it's true, we can take a normal, a little tubular neighborhood out and glue back. You see, when we take a normal neighborhood, a tubular neighborhood out, we must get an S3. And this works if and only if the self-intersection number is -1. It's -1 surgery. Okay, so we do blow out. So given an embedded self-intersection number -1, also symplectic -1 sphere, sigma in the blow up. So, well, this is general in a symplectic manifold, actually. So how does it look? It looks somehow like this. Here is sigma, and then it has a good normal bundle. So here I look at the little bisque bundle, right? And then this thing, you take out, you cut it out. Okay, so what I also need is, since it's symplectic, I know that the integral over sigma of my omega, I mean, I'm here in a symplectic manifold, say. So then this value is some positive number. So now I take this out, and because of the -1, the boundary of the remainder is S3. And actually the foliation is also perfect, so you know how to glue back a closed ball. So you can cut it out. So this here is somehow a neighborhood. And now you cut out. And sew back. So you want to do everything symplectically, and to do because of this, what you can glue back is the ball of capacity A. So, well, this is really as much topology as the blow up. It's not very hard. Somebody with training in topology finds it always totally obvious. Well, me not, but so it's a certain surgery, right? You have an embedded surface. You take out the normal bundle. You try to understand what the boundary is, and you glue back something with the same boundary. And here it happens to be S3. So you glue back the 4-ball and you check sizes, and you also have normal forms near the boundary, and then you know that everything is symplectic and fits together. Okay? Fine. Blow down. So now in our situation, what happens? We have this cohomology class, right? I wrote you down before. And we wish to use it. So what, maybe I should write it again. So what is given in 2? Given is only this alpha, which is a L minus some AJ, BJ. So this we have, but from this we should first conclude that we have for every EJ a -1 sphere in that represents the Poincare dual. If we have that, we can do the blow down. And then this goes away, and we sew back balls, and we get exactly K AJ balls in the blown down manifold, which happens to be CP2, right? So this is the strategy. Okay, we have this class in H2, and we want to argue that every EJ is actually represented by a -1 sphere. Then we can cut it out, and at the end get some manifold with an embedding. So there are 2 things to check. The first one is that these representing spheres do exist. And the second one is that this manifold is CP2. Topologically, it's clear, but there could be another symplectic form representing the same class that is not diffeomorphic to CP2. But fortunately, Gromov-Taubes have proven that there is only one symplectic form up to symplectomorphism in a given cohomology class. So it's actually used here, recognition theorem. If you have a symplectic form on something diffeomorphic to CP2, and you know the cohomology class, then there is a diffeomorphism of CP2 to the usual Studi Fubini form of the same size. So here we need Gromov-Taubes, a theorem about the classification of symplectic forms of CP2. And here we also need Gromov-Taubes. It's not so easy to see that such a homology class can be represented by a -1 embedded sphere. But it is the easiest part of this Gromov-Taubes correspondence. So maybe I write something. So therefore, need to represent these EJs by this joint embedded -1 spheres, let's say symplectic. It follows from a junction formula that if you have a symplectic -1 sphere, it is embedded. It follows also from Taubes' proof that the object, the spheres you get, are embedded. Okay? And this is okay by taus. So you see, I use here something horribly difficult all the time. Taub's Seiberg-Witten theory. We use it about 4 times. And you cannot do these things without it. Also now, there are no ways to do it without it. So this theory is the following. There is a bijection between Seiberg-Witten invariance and Gromov invariance. And what is the great thing about it? Yeah, when you want to do something about in symplectic geometry, very oftentimes you wish to represent certain homology classes by holomorphic surfaces, and these holomorphic surfaces are sometimes guaranteed from this theorem because something on the Seiberg-Witten side is known, and thanks to this correspondence, you know that the classes you wish to have represented are represented by symplectic or equivalently J-holomorphic surfaces of a given or of a not given genus. I just use it here freely. It's of course a bit criminal. It's a black box. Yeah, sorry. By the way, these spheres are all disjoint. And this does not come from Seiberg-Witten, but from positivity of intersection. Because when you have 2 holomorphic spheres in a symplectic manifold for a J that is omega compatible, they must, like in complex geometry, intersect positively. And therefore, their geometric intersection number is equal to the homological intersection number. But the homological intersection number between AJ and AK was 0 for J different from K. So they are disjoint. Otherwise, we mess up when we do the blowdown. Okay? Questions?
Sorry, I have one question. So,
Yes.
So we need to represent the given classes by disjoint symplectic spheres. If the spheres are not pseudo-holomorphic, then a priori it's not clear why they have positive self-intersection.
Absolutely.
If they are pseudo-holomorphic, it's okay. So, but do I understand correctly that Taub's Seiberg-Witten theory makes sure that allows to show that if any symplectic sphere in our case is realized by pseudo-holomorphic curve?
No, not symplectic sphere. You see, the difference between symplectic and J-holomorphic is extremely small. Because if you have a symplectic sphere, you can choose a J for that symplectic sphere so that along the sphere, the J and the omega go well together. And then you just extend it by the flexibility of J's and maybe add some genericity outside. On the other hand, if you have a J that is omega tame, like in the last talk,
yes,
then this holomorphic sphere is automatically symplectic. So the difference between symplectic sphere and holomorphic sphere is totally minor. Just forget about the difference. No difference.
Okay. So
sometimes on the J side you have to say generic, but it's not so important now.
Okay.
But the point is that what I'm given is not any geometric object. I'm given a homology class, and I wish to represent that homology class by a symplectic or J-holomorphic sphere.
Okay.
And this comes from, there is no easy proof for that. For a small case, there are ad hoc arguments. In the old papers before Taub's by McDuff and others, they did something by hand, but it was very tricky. But now it's very general. It just works because the Gromov invariant, the Seiberg-Witten Taub's Gromov invariant of these classes is not 0 finished. It's extremely strong and practical. And you see, I will use it later in stronger forms, so I already use it now. One could do probably without. I'm not so sure. Maybe only for small k. But later we will have no chance without Gromov without Taub's. So I already use it now. Okay, so this was the first step. From 1 to 2, we have translated the geometric problem into the existence question of a symplectic form representing a given homology class. Okay? So what's the time? I should finish. Maybe I should do a bit more. What do you think?
Okay. Yes, so you have still 5 minutes.
Okay, I will just go on a bit because I just want to motivate somehow the most beautiful step. Maybe not the hardest, but the most beautiful.
Mm-hmm.
So the next one is we will translate this into. Here we had given a class, we want to find a symplectic form. And now I will translate that in a purely homological statement. Okay? Is the following. It's that, well, you remember this class? So alpha was this very special class on the k-fold blow up. And I say, in order to have this class represented by a symplectic form, it is enough to check certain homological statements. Namely, it should be positive. This means that alpha wedge alpha is positive against the fundamental class. And that alpha is positive on all doesn't die. Exceptional. Okay, so what is written? You see, before we spoke of exceptional spheres and symplectic forms, which is still kind of geometry. But now geometry is gone. This is completely homological. I'm not speaking about exceptional spheres, but about exceptional homology classes. And the homology class on the blow-up is called exceptional. Well, of course, by analogy of being represented by a complex sphere, saying that the, how is it called? This K thing evaluates to 1, or if you want that C1 on it is 1, and the self-intersection number is -1. You see, if E would be represented by a holomorphic sphere, then this would mean the first Schlenk class of the sphere is 1, and the self-intersection number is -1. But I don't need to think of spheres. It's completely homological. Okay? So I will do the easy part and then the hard part next time. So the proof. Is the statement clear? So what is really important is that this was still geometric. It was the problem of finding a symplectic form. But this is now translated into a statement of this cohomology class evaluates positively on certain homology classes. And you can just find them because you know the homology ring. You can write them down and check, right? This is already algebraic. Okay, so this direction is not so hard. Okay, so you see, here you already see something like in 4. This is the volume constraint, and this is the holomorphic constraint, but written already in homological form. So this is, of course, because when you have alpha square and you evaluate it, right? Well, what is it? If in 2 you have been represented by a symplectic form, yeah, that guy must be positive, right? So this is omega squared over mk. Well, this must be positive because it's a symplectic form. So this is this. And now this. Well, wait. Yeah, sorry, I probably. So this again needs Gromov-Seiberg-Witten-Taubes, because now we need a much stronger statement. So these classes we have seen before, these exceptional classes, they actually were homologically of this type. But now we needed to know for all of them, and there are many more. They are not just the K exceptional classes that fulfill that. But what Gromov-Taubes-Seiberg-Witten tells you is that this representability is true under this condition. If you are, so the one early statement of Gromov-Taubes-Seiberg-Witten theorem is that if you are an exceptional class, you are represented by a -1 sphere, right? So again, by Seiberg-Witten-Taubes, we know that all exceptional classes can be represented by J. So if one writes that, one means by omega tame J holomorphic spheres. And then so therefore it follows that since alpha was omega represented, it means that this must be positive, right? Well, it's just right, by assumption in 2, we assume that alpha is represented by omega, and since E is represented by an omega tame J sphere, it must evaluate positively. Right. Okay, and the other direction, it uses so-called inflation, which is a geometric construction, which is elementary but very nice. And I like it very much because it tells you that traditionally people thought and used holomorphic curves to obtain embedding obstructions, right? To say that certain symplectic embeddings cannot exist. But inflation is a method that tells you that existence of different, maybe, holomorphic curves can be used to construct embeddings. So the holomorphic curves are not only obstructive, but also constructive. And if you are lucky, the obstruction and the construction result to the same number. And this happens here. But the J curves you use are different curves, not those we have used for the obstructions, not the exceptional spheres, but different ones. Okay, so, but probably I have to shut up.
Felix, thank you very much. So let's thank the speaker.
Thank you.
And are there some questions?
Oh, great. Everything was very clear.
Okay, so so if not, so today it was exceptionally at 3:30. And
Right.
but next, because this was our initial schedule, and we just keep it. But and next lecture we again keep our initial schedule, And
Yes.
after tomorrow on Thursday, we will start at 5 p.m. Moscow time. That is 4 p.m. Kyiv time. That's it.
Great. Great. Oh, great picture. Yeah, we have good weather here, I must say. We have even a cafe that is open, but one has to know from